Today we will see the topic about differential pulse code modulation. Generally, in differential pulse code modulation, the principle behind in this that it works on the principle of prediction. The value of present of sample is predicted from the past samples. Then the prediction may not be exact, but it is very close to the actual sample value. Generally, the samples are adjacent samples are often to be a high degree of correlation, and the high degree of correlation causes the redundancy information on the things. So if we have to remove the adjacency redundancy things before encoding we have to remove the adjacent redundancy problems, that is redundancy information. If we remove that redundancy means it's a more efficient coded signal and the result. So we have to remove the redundancies to use linear prediction. This is the main principle behind in that. Especially we encode the E of n instead of M of n, where E of n is M of n minus M of n. This is a prediction signal we having. Next is that what I said is the thing on the upcoming slide. It's a technique that codes the difference between the sample points to compress the digital data. It's more efficient because the audio waves can be predicted in predictable patterns, and it predicts an X sample and codes the difference between the prediction and also the actual point. Since the difference between the samples are expected to be smaller than the actual sampled amplitudes, fewer bits are required to represent differences. Generally, it's for example, if x of k extends over the interval Vh minus Vl, and using a pulse code modulation, x of k is encoded using 2 power 8. If it is equal to 2 power 50, that is 256. So that step size is s equal to Vh minus Vl divided by 2 power 8. That is Vh minus Vl equal to 256 into s. However, the different signal x of k minus 1 extends only over plus or minus 2s. The quantized levels need are plus or minus 0.5s and plus or minus 1.5s. There are only 4 levels and 2 bits are adequate. So the differential pulse modulation takes advantage of higher correlation between the samples by encoding the difference between the samples rather than the absolute sample value. If you can reduce the bit rate by about the 25%, that is by using prediction based on the previous samples, it's only since only the difference between the predicted and the actual values, that is maybe it's 4 bits per sample. We will see the upcoming slide. Okay. Next, the overtime. The error between the decoded signal and the differentially encoded signals are increased. So the periodically full phase is pulse is sent rather than the difference. The extension of pulse code modulation, which differentially encodes the data to increase the transmission efficiency. Differential pulse code modulation is used in many image video compression algorithms, including a JPEG image also. The principle behind the differential pulse code modulation is that the source data is likely to be analog signal. So it will be an analog signal, which is likely to we have to change the amplitude quite gradually. We will change the amplitude. There are unlike to be a large jumps in amplitude over a short time. Certain times it will be maybe a large jumps in amplitude. Therefore, the signal can be we can represent it by initial value and some incremental deltas against these values. So if I such these, the difference are likely to be small, and therefore the throughput may be the result is increased. So the encoded such a signal, it will give a good result. This is the diagram structure for encoder and decoder. This is a block before encoding and decoding. There is a process we adding a predictor process. So here it is used to remove the redundancy from a data stream. So we have to in higher correlation with results redundancy already I said. So from that redundancy we have to remove the redundancy information. So we have to remove redundancy means that is the input data stream by quantizing the difference between the current input sample and the linear prediction of the sample. So this is a basic structure for encoder and decoder. Here see that the predictor and adding by here we are in encoder adding a predictor before the encoding process, and also in a decoding process before decoding we add a predictor. Okay. Here this is a given sampled signal and the result signal. For the given input signal, the sampled values are 1, 2, 4, 5, 6, 9, 7, 4, 0, 3, 5, 6. Here the encoded using a standard pulse code modulation, the data set would require log of 2 of 9 equal to 1, that is 4 bits per sample. However, the delta between the two samples never less than or minus 3 or greater than plus 3. It gives a range of 7 values which can be encoded as a 3 bits per sample. If encoding scheme used was a differential pulse code modulation, the output would be here. See this. For one, it is a delta modulation or pulse code modulation, the values changes 1 to 1, that is minus 3, minus 2, like that. Here the differential pulse modulation process, the difference between input samples are minimal. The differential pulse code modulation is used to calculate the difference and transmit a small difference signal inside the input sample signal. Here the difference between the input sample is less than the entire input sample. The number of bits required for the transmission is reduced. So this allows for a reduction in the throughput required to transmit the voice signals. Generally the DPCM can reduce the bit rate of voice transmission, that is down to 48 kbps. Here in differential pulse code modulation there are 10 steps. We are having a process, that is process steps. First one is with comparing with the diagram, it's a very easy steps we have to see in upcoming slides. The input sample is input signal is sampled at a constant sampling frequency. This is a first step, the twice the input frequency. Next is after the sample, the samples are modulated using the pulse amplitude modulation process. At this point only the delta processing, that is a differential pulse code modulation process, takes over. Here the sampled input signal is stored in what is called predictor. The predictor takes the stored sample signal and sends to its differentiator. Next, that the differentiator compares the previous sample signal with the current sample signal and sends the difference to the quantization part and coding as phase of pulse code modulation. Next is that after quantization and coding, the different signal is transmitted to its final destination. After the final destination, once the signal is received, after receiving the end of the network, everything is reversed. First the different signal is to be dequantized. After dequantization, then the different signal is added to the sample signal stored in a predictor. Resulting signal is sent to a low pass filter that reconstruct the original input signal. These are the first 10 steps. That means that these are the short steps for understanding the differential pulse code modulation process. Here this is a differential pulse code modulation system, that is a transmit side and receiver side. Here the difference between the, we will see about, first we will see about the transmitter part. Here the difference between input signal and the reconstructed signal. Here the input signal is xi of n of ts, reconstructed signal, that is x bar of nts. We will use a x bar of nts, okay, or x. We will upcoming slide we will say that reconstructed signal, what is the input signal, okay. Generally the x of n of ts, that is xi of nts, is the input signal, okay. M bar of n, that is a reconstructed signal, we have to see. Here the difference of the signal from the sampled signal and the prediction filter from the signal, E of NTF is a difference, E of NT is quantized by the quantizer. Here the predictor generator presents the estimate of the signal from the quantized difference and previous estimates. So here this is the signal. Next the DPCM receiver. The predictor generates the present reconstructed signal, that is x bar of NTS. That is, okay, here the notation is changed. So the predictor generates a present reconstructed signal from its previous values and incoming DPCM. So the reconstructed signal is more accurate since the predictor will consider the complete history of the reconstructed signal. So this is the thing we have in a process of transmitter and receiver. We will see about that here. And in generally in quantizer process, the input signal is E of NTS. The input signal is E of NTS equal to, that is Xi of NTS and Xp of NTS. So Xp of NT is a predicted value. Here the Xi of NT is a sampled input. And here E of NT is called a prediction error. Here the E of NT is a prediction error, the amount of by which Next is that let the quantities input that is output cache to be defined by a non-linear function q of dot. So the quantization output is take it as v of nts. Here the indication knows that v of nts equal to, that is a quality quantizer factor q dot. So therefore take it as q of e nts, that is equal to e of nts plus q of nts, where q of nt is a quantization error. The quantization output v of nts is added to the predicted value, here u of nts equal to xi of nts plus q of nts. So we have to the predictor to produce a predictor input is u of nts equal to xp of nts plus v of nts, where u of nts is equal to xp of nts plus e of nts plus q of nts. So we will know xp of nts is a predicted signal, e of nts we will know that the prediction after that signal, q of nts is a quantization error. Therefore we will get as xi of nts plus q of nts. The irrespective of the properties of the predicted of the quantized signal is differs from the original input signal by the quantization error. So the output at the receiver generally differ from the original input only by the quantization error occurred as a result of quantizing the prediction error. These are some real-time examples. We will see this later. The differential pulse code multiplication, the receiver side, the output signal is quantization radius defined as SNR equal to sigma x square divided by sigma q square, where sigma x square is the variance of the original input signal, and q we will know q factor, that is q is the variance of quantization error. Therefore the sigma square is a quantization variance. Therefore SNR equal to sigma x square divided by sigma e square into sigma e square divided by sigma q square, where Gp is the prediction gain produced by the differential quantization scheme. So this is the delta pulse code modulation process. Here these are the things, certain things we have to be noted, that some quantization error occurs will be here. So from these we will move to into the delta modulation. Okay, thank you for this presentation.